Okay, thank you very much. So this is a joint work with Lukas Brenner, who is sitting here in the audience, Xavier Quattrochoa, and Robert Koenig. So here is a sketch of a quantum computer, which is built in a scalable way based on some DiVincenzo criteria out of these transmon qubits. But if you look closely into these transmon qubits, they are actually continuous variable systems. And what we typically do is we do something which you can call qubit to oscillator encoding, where you pick two eigenstates out of this oscillator and you associate them with the 0 and 1 computationally basis states of the qubit. And here in this talk, I would like to invite you to maybe think about whether we can use these continuous variable systems differently, and maybe whether we can use their potential more. And what we did in our work is that we have a continuous variable quantum algorithm which uses 3 oscillators and a single qubit, and can be used to factor any integer n in the polynomial number of elementary operations that I will define soon. So let me compare it to Shor's algorithm. So our algorithm, our algorithm has the constant number of the resources in the physical system. Those are these 3 oscillators and a single qubit, while for Shor's algorithm, this scales with the number or with the bits of the number that you want to factor. Okay, and okay, I don't know what's happening. And I want to point you out to these distinctions. So we are here using n-squared elementary operations, while the Shor's algorithm uses n-squared log n gates, if you use the best algorithm for multiplication of integers. And while this may sound like not much of a difference, this is an indicator that we are actually using some benefits of these continuous variable systems, and our algorithm is not just simply oscillator encoding of the Shor's algorithm. And here is a disclaimer. Our algorithm should be understood primarily as an exploration of an abstract model of computation rather than an experimentally viable road to factor some practically relevant numbers, such as the ones that you find in current RSA systems. Okay, so the physical system that we use is qubit oscillator system, and we take operations which are readily available experimentally in the present setups, such as an atom in an optical cavity, which can be described by this Jaynes-Cumming Hamiltonian. And if you want to know a bit more about those, there is a beautiful review paper by Liu et al. From the last year about these systems. So what are the available operations that we will use? So on the oscillator side, we will use basic linear optics operations. On the qubit side, we will use single and 2 qubit unitaries, and we will have also this interaction between them, which is probably the most interesting part of this. So let me go over them. So from the linear optics, we are using the preparation of the vacuum state and these generators of the Gaussian unitaries, which we require to have bounded strength. So we will have single mode squeezing, single mode phase space displacement, rotations, and also 2-mode beam splitters, all of bounded strength. And we will also consider the position and momentum homodyne measurements. And for each of these elementary operations, we will count them as a unit of complexity. Okay? I don't have to tell much about the qubit operations. I just mentioned that for our algorithm, we only need the preparation of this computationally basis 0 state and a Hadamard gate. Okay, and so the most interesting part is this interacting term, where we use qubit-controlled phase space displacements and qubit-controlled phase space rotations. And both of those are experimentally available. And we will again count each of them as a unit of complexity. Okay, so now I would like to revisit these operations, and I would like to argue that they actually, in some very natural way, implement arithmetic operations and maybe some extended arithmetic framework. So this is a bit unhappy. Okay, I don't know what to do with this. So first of all, you can implement multiplication of a position state by a constant by doing a squeezing operation. And you can also implement addition to position of a constant by doing a displacement. And you can also do it for non-constant parameters by decomposing them into the elementary operations that I showed you. So for these, either for the multiplication or addition, we need the logarithmic number of elementary operations with the parameter that we want to implement this operation with. And the last operation that is from this arithmetic framework is something which is called bosonic addition, which basically takes the position state in the first mode here on the picture and adds it to the position of the second mode. And this again can be decomposed into the constantly many squeezings and the beam splitters. Okay, but we have actually more here. And so we can, in a very natural way, implement Fourier transformation over the real axis. This is basically, so if you implement momentum, homodynamic momentum measurement, then what this basically does is the same as if you implement the Fourier transform over the real axis and then measure in the position space. Okay, and this is again implemented by a single elementary operation. And additionally to this, we can also add the value of the qubit into the position of the oscillator, and we can also subtract it. And we have these kind of composed operations, which if we have an integer position in the oscillator, we can extract the least significant bit out of this position by doing this operation. And we also have this composed qubit-controlled multiplication operation, which we used in our algorithm. And the last primitive from this that I wanted to revisit is something which we called modular measurement. But this is not new. This is actually, if you know GKP error correction, then this is basically a stabilizer measurement circuit from there. So this uses a resource state, which here is the ideal GKP states, which is a formal superposition over all integer positions, which looks like these delta peaks here. And this is a resource that we use. Then we increase the spaces between those delta peaks by doing this multiplication operation, this mn here on the picture. And we add the position from which we want to compute the modulo into this mode. And if we measure in the position space, the second mode, we obtain some W, and this will have the same result of modulo n as the position state in the first register. Okay, so let me briefly remind Shor's algorithm, and then I will tell you how we modify it to our algorithm. So Shor's algorithm basically, in the first stage, it uses the reduction from the integer factoring into a period finding, where we have this modular exponentiation function, and we want to, if we start with some random h, which is from the multiplicative group Zn star, and we are able to find a period of this function, which will have this form, then we can, with high probability, factor the integer n. And this is exactly what Shor's algorithm does, is to find this period. So we prepare some uniform superposition over some large number of power n, power of two numbers. And then in a coherent way, we implement addition by this function, this modular exponentiation into it. So I depicted it here on this circle where we have these Q elements, which are the circles, and I mark them by these colors, which represents what is in the second register. This is the a to the x modulo n. And so if you measure the second register, then what you obtain is that this colorful state, it collapsed to this periodic state with this shift. And you know that Fourier transforms are really good in extracting information about some periodic signals, and this is exactly what is happening here. So if you do Fourier transform and then you measure in computationally basis state, then you can do some post-processing algorithm, and what you can get is that you will be sampling over almost uniform superposition over elements j over r, where j goes from 0 to r minus 1. And if you can do this, then you can use these samples to recover the period r, and thus factor the number n with high probability. Okay, so in our algorithm, we don't do the operations over the cyclic group, but we will implement them over the real numbers. So here I will compare the Shor algorithm to some very simplistic or idealized version of our algorithm, but it will nevertheless be useful to illustrate the differences. So first of all, we will not start with this uniform superposition, but we will start with this resource states, which is this GKP state. Then we will not implement the modular exponentiation, but we will implement the real exponentiation, where the second branch is there for some technical reasons to do something with the negative numbers. And then we still have to recover the modularity, which we do here by doing this modular measurement circuit. And last here, we don't do the discrete Fourier transform followed by computationally basis measurement, but we just measure the position, we just do the homodynamic position measurement in our circuit. Okay, so you can again go over this circuit and see what is happening here. So for example, here we have this GKP state and the GKP state, which is multiplied by this n spacing, which we will then use to implement this modular measurement. Then in coherent way, we compute this exponentiation to this GKP state. And by the stabilization properties, we can compute that this is actually same as if we add the modular exponentiation to it. And you can obtain that we actually have the same or similar result to what we had from the previous slides from the Shor's algorithm. So if you do this momentum measurement, then what you will be getting are 1 over r z samples, uniform samples from 1 over r z. And such samples can then be used to recover the period r and thus factor the number n. Okay, so this is a very simplistic circuit, and it fails to be physically realizable for two reasons. So first, these GKP states, they are unnormalizable, and we need to use approximate GKP states. And for this, we had to design a protocol to somehow prepare them efficiently, because we need them with very strong parameters. And you could see a talk by Lukas Brenner earlier today about our protocol and also about our complexity lower bounds for the preparation. And we also showed that our protocol is optimal. And the second part why our circuit is not physically realizable is this idealized unitary, which we replaced by something which we called pseudomodular power. And yes, so this leads to this increase of the number of the bosonic modes. And we can decompose this pseudomodular power into the elementary operations, and we can, and the key feature of this pseudomodular power is that if you take the modulo n of this pseudomodular power, it will be the same as if you take the modular exponentiation. Okay, and this unitary is basically implemented by doing some kind of bit-by-bit multiplication by these factors in this pseudo-modular power. I'm sorry, it's not visible. Okay. Yes, so, and the rest remains the same. So we have to do some kind of classical post-processing, but the rest is the same. And we had to analyze the circuit and to obtain the theoretical guarantees and to obtain our results. So let me conclude. So, so we put the qubit oscillator systems and the experimentally available operations at the center stage, and we find an algorithm which uses 3 oscillators and 1 qubit and can be used to factor any integer n within a polynomial number of operations. And so I mentioned in this disclaimer that there are some caveats, so let me summarize them here. So while our algorithm uses polynomially many of the active or squeezing operations, it produces states which has extensive energy in the number n, which we want to factor, which means that the energy is exponential in the number of bits of this number in the computer science terms. So this goes into an immediate open question whether we can have some trade-off between the total energy and the number of modes. And the second caveat here is that we only consider a noise-free scenario, and important question is how we can achieve qubit oscillator fault tolerance, how we can design fault tolerance protocols in these compound systems. Okay, thank you very much.
The session is open for questions.
Thank you for the talk. The question about the energy, I guess, is pretty relevant. I was more curious as well, if you have the GKP states you described and you have your Gaussian tail, this would mess up all the arithmetic to some point, right? So can you maybe comment on how big does how far away does the tail need to be for everything to work? Does it need to be order n repetitions of the GKP, or?
Yes, so the parameters of this GKP states are here. I don't know if you can see it, but we basically show that, I don't know, these exponentially small tails, they don't matter for our algorithm, but these GKP states, they have to have very, very good parameters. Like they are basically this kappa and delta, they are exponential in the number of bits that we need for the algorithm to work. Yeah, especially the one which is larger is the one which is used to implement these modular measurements, because you need the stabilization properties if you add there this pseudo-modular power.
Correctly, then it's like size of the number to the minus 16 or something. So kind of more than quartic, or?
Yeah, it is. Okay, so in terms of the number that you want to factor, this would be n to the log n, okay, where n is the number you want to factor.
Thanks.
Yes.
It's really nice for people to think about doing computation with other kinds of quantum systems. This is something I like a lot also. I was also going to ask about the energy thing, but I guess you kind of flagged it. I remember also, I think, like when it appeared on Cyrate, Aram Harrow had like directly asked about this, I think. So it's like a very important point. So this trade-off would be cool. If you guys have any insights on that and you could quickly comment, I would appreciate that. But do you imagine that the same setup can be used for other problems of interest? So like any hidden subgroup problem could be solved here. Are you guys thinking about other problems? Yeah.
Yeah. Like for this kind of problem, we really like heavily use this arithmetic framework, which somehow comes naturally in this. So, yeah, I mean, you can have like a universal simulator in this, but yeah, I don't know. Like I think that if you really want to get some kind of difference. Like what we have here, this n squared versus n squared log n, this is really achieved by the fact that you can somehow, in a very natural way, implement these arithmetical operations. So I somehow see this.
Yeah, thank you. You mentioned that this proposal is not practical, more theoretical. Is this due to these caveats, or there are other considerations that you have to take into account?
Yes, basically because of those two. Like mainly I don't know, from this energy point, we somehow believe that even like factoring some modestly small numbers like 21, which is the largest number factored by Shor algorithm in experimental setups, would be quite challenging with this approach. But then you also have these noise considerations, because this noise gets like multiplied over this, so we really need some fault-tolerant schemes to deal with the noise. Yes, so that's for those two reasons.
Okay, thank you.
Thank you.